Welcome to The Explainer. Today, we're jumping straight into a massive, fundamental physics showdown between two of the absolute greatest geniuses in human history. We're talking about a battle over the very fabric of reality, the strange behavior of the quantum world, and the ultimate speed limit of the universe. Honestly, it's a debate that determines whether the reality you see around you is actually what it seems to be.
Okay, let's dive into this. Before quantum mechanics got truly strange, Albert Einstein laid down a sacred, unbreakable rule. Absolutely nothing travels faster than the speed of light. He realized that even gravity is an instant. Think about it, if the sun just suddenly disappeared, the Earth wouldn't instantly fly off into deep space. Instead, that change in gravity would ripple through space-time like a wave, and it would take exactly 8 minutes for that effect to reach us. That delay is crucial. It ensures that cause and effect actually makes sense in our universe.
And this brings us to a massive divide in physics, which was perfectly showcased at the legendary 1927 Solvay Conference. It was basically a heavyweight boxing match of physicists. On one side, Einstein demanded a local universe. That simply means effects have to spread from place to place, right? And they have to do it at or below the speed of light. But on the other side, the brand new theory of quantum mechanics was proposing something deeply, deeply unsettling, a non-local reality. It basically suggested that measuring a particle right here could instantly influence something all the way across the universe, completely ignoring that cosmic speed limit. Now, Einstein absolutely despised this non-local idea. It was a core part of the so-called Copenhagen interpretation, which was championed by physicist Niels Bohr. Einstein felt this was just intellectually lazy. In fact, he famously, and pretty dismissively, called it a tranquilizing philosophy or religion. He strongly believed that if your theory required some spooky, instantaneous action across vast distances, well, it just meant your theory was incomplete. You were missing a piece of the puzzle.
But Niels Bohr, he saw things completely differently. He flat out stated, "It is wrong to think that the task of physics is to find out how nature is." For Bohr and his followers, the whole job of physics was just to predict measurements in the lab. And honestly, quantum mechanics did that incredibly well. But asking what a particle is actually doing when you aren't actively looking at it, to Bohr, that was basically philosophical nonsense. And man, that fundamental disagreement set the stage for a lifelong rivalry.
So how does this actually look in practice? Well, in 1935, Einstein and his colleagues published a landmark paper to highlight a phenomenon we now call quantum entanglement. Just imagine a photon splitting into two particles, an electron and a positron. Now, to conserve the total spin in the universe, if the electron is spinning one way, the positron absolutely must spin in the exact opposite direction. Their states are entirely fundamentally linked to each other.
And here is where Einstein laid his brilliant trap. He said, okay, imagine you separate these entangled particles by millions of miles, and then you measure the electron. Bam, you instantly determine its spin. But according to Bohr's rules of quantum mechanics, that means the faraway positron's wave function has to collapse instantly so it can take the opposite spin. Einstein argued that this spooky action at a distance clearly violates the speed of light. It's a paradox. Therefore, quantum mechanics must be flawed, or at least incomplete. And this brilliantly illustrates Einstein's incredibly elegant alternative, the local hidden variables theory. Instead of spooky action, imagine the particles touch and secretly coordinate their spins before they ever separate. It's exactly like writing their coordinated spins on a piece of paper, sealing them in little envelopes, and then sending the particles on their way. When you eventually measure them, you weren't instantly influencing the other one at all. You're just opening an envelope. No faster-than-light communication needed whatsoever.
Tragically, Einstein died without the physics community ever truly believing him. For decades, physicists largely just ignored that 1935 EPR paper. Why? Because both theories, Einstein's local envelopes and Bohr's non-local weirdness, predicted the exact same experimental results. That is, until 1964, when a fiercely clever physicist named John Bell dusted off Einstein's forgotten paper and finally figured out a way to actually test it. Bell's absolute genius was adding a twist to the theoretical experiment. He realized that if experimenters independently chose the axis they used to measure the particles, say they randomly shifted their measurement dials to different angles like 0, 120, or 240 degrees, then the local theory and the non-local theory would finally yield completely different results. They couldn't hide behind the exact same predictions anymore.
Let's look at the math here because it's fascinating. If Niels Bohr's non-local quantum mechanics was right, where measuring one particle instantly forces the other to collapse across space, the math perfectly predicts that when experimenters independently choose different measurement axes, the results from the two particles will disagree exactly 25% of the time.
So the crucial point is the alternative. What if Einstein's local hidden variables theory was correct, meaning the particles pre-planned their answers in those little envelopes before separating? Well, the mathematical minimum they could ever disagree would be roughly 33% of the time. There was literally no mathematical way for local particles to fake that 25% rate. The trap was set. All scientists had to do now was run the actual physical experiment.
It took decades of technological advancement, but physical experiments finally caught up to Bell's math. Physicist Alain Aspect pulled off an absolute experimental tour de force. He used a special pair of crystals to shoot thousands of entangled photons per second down two separate distant paths. At the end of each path, he placed polarizers that could independently rotate to different measurement angles, perfectly mimicking John Bell's proposed test.
And the results were absolutely stunning. Measuring thousands of pairs every single second, the disagreement rate was exactly 25%. It matched quantum mechanics perfectly. Einstein's local hidden variables theory, the whole idea of the envelopes, failed completely. This experiment definitively, conclusively proved that there really are faster-than-light, non-local influences happening in our universe.
But, here's where a lot of physics textbooks actually get it wrong. They often misunderstand Bell's theorem, claiming it just ruled out local hidden variables, and that's it. But what it actually proved is much wilder. It proved that nature itself is in serious, fundamental tension with the theory of relativity. Einstein might have been wrong about his specific hidden variables idea, but he was entirely right to be worried about non-locality. The universe really is spooky at a fundamental level.
Now you might be sitting there wondering, wait, does this break reality? If influences are moving faster than light, shouldn't we have crazy, catastrophic time travel paradoxes? Thankfully, no. While quantum mechanics definitely violates the spirit of relativity, the actual measurement outcomes are completely random. Because you can't control whether you get a positive or negative spin, you can't use this instantaneous connection to send a faster-than-light text message. Our causality is safe.
Now, what's really interesting about this slide is the possibility of a massive, bizarre loophole we might have missed. Remember, Bell's mathematical proof assumed that when you measure a particle, there is only one definitive outcome, which forces the wave function to instantly collapse across the entire universe. But what if we just remove wave function collapse entirely from the equation? Could that somehow save Einstein's dream of a purely local universe?
Enter the many worlds interpretation. In this absolutely mind-bending view of quantum mechanics, when you measure a particle, the wave function doesn't collapse at all. Instead, every single possible outcome happens simultaneously. By observing the particle, you actually become entangled with it, and reality itself splits. There are now parallel physical versions of you experiencing each possible outcome.
Let's compare these two worldviews because it's wild. The Copenhagen interpretation requires this instantaneous wave collapse across vast distances, making it heavily uncomfortably non-local. But the many worlds interpretation? It's strictly local. No faster-than-light communication is needed to coordinate distant particles, because versions of those particles and versions of you measuring them already exist to account for every single possible outcome right off the bat.
Which leaves us with this final, incredibly provocative question. Do we really live in infinite parallel universes, branching out by the millisecond, simply to preserve Einstein's universal speed limit? If many worlds is correct, that immense, terrifying conflict between quantum mechanics and relativity just completely vanishes. It